What's up? What's up? All right. I don't know how in depth. Oh god, I forgot about this. Where's the script running? There you go. I'll kill the bot. Sorry, I still linked the only zeros chat. But yeah, I don't know at what level of like how much you do or do not know. Like, do you know MIPS? Like how like ASM works and stuff like that, or you like have, or do you just like don't understand how to like read OT stuff specifically? Okay, so you've done some ASM stuff. Okay. All right, so you're like familiar with like branch delay slots and how to read ASM and so on and so forth. Okay, so let's talk about OT structure. I don't know if I have tabs open for this. File list is good. There's a thing in here for. So there's some stuff in here you do, some stuff you don't need. I don't need a scene table. Don't really need that anymore. Save context, entrances. I always forget the things that... I always end up reopening these tabs a million times anyways. Alright, so... so the way files are stored... I'm trying to get to... There's like a DMA table, which you may or may not really need to look at too much. But basically the way a DMA table works is that... Really? So 2 words? File system, sure. Okay. So the way it works is that there's a starting, it's at this address. So here, let me just load up the ROM. It'd be actually a really good way to view it. So I pretty much always set my byte group size to 4. It's like very little reason for OT, because MIPS is 4 byte aligned. All the instructions are always 4 byte aligned. So when generally you're looking at code, you just want to look at it this view. I use HXD. I'm sure there's other decent ones, but this one's been pretty great. Anyways, if you go to this address, this is a DMA table. The way the DMA table is structured is just a DMA table is just a list of all the files in OT. The first 2 values are just the start and end address in ROM, and for you, or for most people, the second address, the first one's for the actual ROM address, and the second one is its virtual ROM address, its VROM address, and this last value is going to be 0 if it's compressed or not. So basically the way it works is for all of these, because we work with an uncompressed ROM, the start address for the ROM and virtual ROM are always going to be the same. The virtual ROM is basically if you just take the compressed ROM and uncompress it completely. That is like what the virtual ROM space is. So those are always going to be the same because we're working with the uncompressed ROM already. If they were compressed, this will have like the actual address values. So like has the virtual addresses and the physical address. And this physical address is always 0, just means it's not compressed and the game doesn't try to decompress it. Anyways, this isn't super important. There's a page here called file list, which just has this DMA table, which is a list of all the files. And like the files aren't named or numbered. They're just the addresses in ROM of where the file is. So like whenever the game says like, hey, I'm going to load some file, it just says load the file at blah address, and it'll just load that address. Anyways, there's this file list that just has this information. This start and end matches this data here. The size is the difference between these 2 numbers. So this is pretty good for finding files. If you just want to search for a file in ROM, like you're looking for a particular file. So go ahead and do it. The thing it doesn't have though is the RAM addresses. So this is just where the file is in ROM. It doesn't tell what the virtual RAM addressing is, which is important. I'll get to in a bit. So it's pretty useful if like you like know some piece of code is like relevant, but you don't know what file it's in. You can like look here in this DMA table, say like, oh, it's most likely going to be in this range here. Zoom in a little bit. It's gonna be like in this range here. It's probably gonna be in the main game code. There's like the core game engine here. It's gonna be pretty much all in this file. But occasionally you'll find something in some other file, like Kaleidoscope is the pause menu and so on and so forth, depending on what you're doing. But typically, what I usually end up working with is most of the time you're working with the actor files. So the actors are after these initial all these initial like base game files. There's all the actor files, which each have their own code file. And after all and they're all together. And after actors is like the objects, which isn't code really. It's just object data, like graphic data and stuff like that. And then you have textures, which is more of that. And then here's all the room data. So the game's actually pretty structured pretty well. And like the scenes are always first followed by all the rooms for that scene. So the game is actually pretty well organized. The game likes the scene files and a lot of files. They likes to kind of have them all starting at like 000 at the end, so they're all like aligned to the thousandth. Which means that a lot of times there's a lot of space between all these files. And at the end, these are all unused files, which I think Rando actually just deletes all these all these addresses. But the first set of files, they don't put any gaps. They're all back to back. So you notice that these addresses are like all back to back. And they're like weird values. They always have to be aligned to the 0. But apart from that, they're just whatever they want. So if you need to expand a file, you're kind of screwed. Same thing for actor files; they're generally all back to back. So if you need to expand a file for whatever reason, you're going to repoint the file. Now, I would say this probably isn't super relevant to you, but I'm just giving you kind of a general idea of like how the structure of the game works. If you want to look at how that was done a little bit, we can get to that. But for now, let's just focus on trying to read a particular file. So there's another page I like to look at called the actor overlay table. So there's a separate table that has all the actors sorted by their IDs. It's in the same order, but whatever. So whenever you like say load actor, like say like 49 or whatever, it has the address. It basically has the DMA entry right here. It has like, it says where the file is, and it'll do the DMA. But after it has more information in this thing. So this first part is part of this table. I think the rest of this is not. I think it's extra information. But it has the VRAM address. And this is important because basically the way that files work is that all the files basically assume that they're laid. The game assumes that you have like this full RAM address called virtual RAM that goes from, all the way up to, it has the full range, way more RAM that actually exists, right? And then all the files are like loaded back to back, effectively, just like all loaded at once into this VRAM space. And then they're saving the ROM at a totally different location. And so what ends up happening is whenever you load a file, where the file gets loaded into RAM is just up to the allocator. So the file can be loaded into any location pretty much in RAM. So what it does is that anytime there's a pointer, it modifies the pointer based on like where it gets moved to. So let's say that it says the file here starts at 808E4190, and let's say it gets put at like 808F4190. That means that all the pointer references in this file are going to get added like 10,000 or whatever that number is. It gets 10,000 added to every single pointer into it. So when you're looking at, if you look at the code of all the pointers references, they're always going to be in VRAM addresses, which are going to be this weird number that is not used pretty much anywhere. And honestly, I kind of hate the whole system, and it's stupid and dumb, but whatever. VRAM should always start at 0 in my opinion, and I think whatever, their compiler is stupid. That's fine. Anyways, the point is that generally what you want to need to do is that whenever you look at their VRAM addresses, you'll need to subtract this base VRAM address from any address you read, and then add the actual base ROM address, and that gives you like the absolute ROM address of that pointer. So I'll go over this again, like when we look at some pointers. Anyways, the next part here is this thing here is every actor has this thing called I think it's called like an initialization table. But basically there's a pointer. Again, this pointer is gonna be somewhere in this file, and it's gonna be a table of information that that every actor has. Every actor has this like structure. So if you go to the actor page, they talk about it, and it's this structure right here. So the first thing is the ID. It's like not, most of the stuff is pretty not important. The only thing that matters are these last 4 values, and honestly really just this one and this one. But this is the most important one. It has a pointer in the structure to where the initialization function is, so that when the game loads the actor, it knows what function to call. And it's great for us because we are looking for the init function. It means that we can just look at this pointer, and that just tells us what the file is. So let's keep that in mind. I usually have a lot of trouble finding actors, so I open up the actor list page, which just has all the actors. So if I look up like Mito, so Mito is this actor. The file name is enmd. If you're curious where these file names came from, they're from the debug ROM. So in the debug ROM, every file has a name, but that's all stripped in the release version in 1.0. And as we're looking for this file here, ID 160. So if you look at the actor table, here's the actor we're looking for, right? So at this point, a lot of times I do this by hand. So I'll show you like the 2 ways to approach this. I'll first show you what I do. So first of all, I have this file somewhere. I always have a lot of trouble finding it. I got it from MZX at some point. All right, this thing. It has a list of, it just has a disassembly of every overlay file. Actually, of every file, it even has like boot and code in here. So it has everything in here. So if I look for, it's nice. It has errors in it. It's not always right. Anything involving floating point, I notice is not disassembled correctly. It also has like, I don't know. There's some nice things about it. There's some bad things about it. Because nothing's in ROM addressing, it's like I always have to look up the things anyways. So, but it's nice sometimes I do when I just want to get a good start. But we're looking for MD. MD here. Okay. So this is the file. I could probably say this is MIPS. Anyway, so here's the actor file. This one's like nice because, so whenever you're looking at the code, there's certain patterns that the compiler always does. So first of all, every function will always end with a JRRA, followed by it won't always be a no-op. Sometimes there'll be an instruction there, but there'll always be a JRRA at the end of a function. Typically, there's a couple of things. It'll never branch outside of a function. So branches are always self-contained in their function. So if you ever see a branch jumping down really far, you know that wherever it's branching to is still like, that means that function's like really big. It also means if you see a JRA, there's only one JRA. There's never more than one. They never put returns in the middle of a function. If something returns out of the middle, it always branches to the return instruction. So it gets a really good way to just like, so in here they have it already split up by the functions. Like, okay, well, here's the start of the code, and here's like a JRA, and down here, here's the next function. They just keep going until there's another JRA. There's a couple other things. The stack, for example, there's always going to be a like subtract from the stack pointer at the. So if a function calls another function, it always adds the stack or subtracts the stack pointer, and then at the end of the function, it'll add that back in. So you'll always see that pairing. So if you see like a function that says like if you look at your function, because it's really easy to find the ranges of the function, because you just need to look between this JRA and the previous JRA, and that's the range of the function. And then you just look for like, okay, are they adding to the stack? So if they add to stack, then it means that there's going to be a jump. So here we can see just a JL here. There's actually a few JLs. And it also means that you can add more JLs safely because it's already adding to the stack. If there isn't a JL already and there's no stack manipulation, it makes injecting into that function harder. So that's something to keep in mind. So like in the first function here, for example, there's no function calls, so there's no stack manipulation. So it'd be really hard to inject into this function. But that's the general idea. This, like, just kind of the functions are enabled. Every label here means that there's a branch to it at some point. So that's kind of nice to have. But at some point, there's going to be an init function, which is going to be here. And that we can look through here. And you can look at the init function. It's actually fairly long. Different actors have short or long ones. Mito is kind of awkward because Mito can show up. Remember, Mito, they have the same actor for Mito showing up in both sides of Kokiri Forest and in the Lost Woods and credits, and I don't even know where else, right? So there's going to be some scene checks in here and probably some checks about in his house. And because of Kokiri Forest, there might also be some checks about the position, because like I don't really know. Maybe the two Mitos are different variables. I don't really know how the Mitos work specifically because I haven't looked into this. But that's the idea. But like supposedly be somewhere in this range. But no matter what, anything that Mitos like changes based on blah blah on his init is going to be referring to the save context. So a lot of these functions have so in MIPS, the A registers are like the arguments, the things are passed into function, and V's are the return values, and T's are just temporary. So A's are already set when you enter here. I always get these mixed up. I think A0 is a reference to the actor to itself, and A1 is a reference to the global context. It might be reversed. I know in init and in the main function, they're reversed for whatever reason. It's not consistent and it's annoying. But A2 and A3 aren't used in these function calls. But that's something to keep in mind. But there's nothing passed in for save context. So it'll have to load in save context at some point during this code here. So if we look for the save context, like, I don't know, 11A5D0, here we go. We're loading the save context here. So we're only loading this one spot here. We notice that we're loading this V0 here twice. That's probably because there's a branch likely or a branch right around it. Possibly. So yeah, here there's a branch. Yeah, and then there's another branch here. The compiler is pretty bad. So the second V0 is not needed. Since it's already set here. Well, I guess I could skip over this line. Anyways, the point is it's loading V0. ED4 is in the range of flags, save flags. If you look at the save format, so ED4. Mito tree, probably this one. It ends it with 10. So this thing always kind of bothered me, the format of this thing. I wish this was in like the bit mask. I think these are all 2 bytes wide. So I think it's here, and then 10 would be this one. Showed Midas Sword and Shield. So right here. So that's what this check here is. As that checking for this bit. And down here, we're also checking for V0. I mean, the key thing here, we really should be looking at V0 here, because V0 maintains its value. So here ED4 again, and then that's in T4, and then that gets ANDed with 10 again. So same value that gets put in T5. Here's in T2 or T3. So there's actually like the same check in a different place. And then there's a branch likely, which are always gross. And then again, you have another V0 check for A4. A4 is going to be, I think, in quests or something like that. Oh, God. A4, quest status. This doesn't actually have a description of this. A lot of times for this stuff, I just go to this file. I always look for age. It seems to get me there fastest. This is the Z64, which is in the rando. Anyways, here's the quest stuff. With EDC. Oh, that's good to know. So this is checking for some quest status. It's checking for it ends with T6, which is this value. So it's reading this from a table. Which is kind of unfortunate. Hey Krim, what even is that? A notebook. I see. Anyways, that helps a lot because then you can search. You can just search for EDC. That is not an E. Okay, so there's a few EDC checks. They're just these 3. So the fact that it's checking for EDC means one of these. There's one extra caveat is that OT is very inconsistent about this, but there exists a function that you can call that you pass in the event flag number, and then it will returns whether or not that event flag is set or not. So instead of loading the whole byte and then masking it and then checking that, it'll just you load in the number, you call the function, and it returns true or false. 2A8B4. So that's another function to look out for because it won't show up. Clearly, they're not using that because they're just loading EDC, which makes things easier for us. But yeah, we have EDC, and then we're just masking it with 1 in this case. But this isn't at the init code, so we have to be careful. This is like in some middle code. Trying to figure out like where this code gets called is gonna be a little tricky. Again, we're checking this thing. We mask with 1, and here we mask with 1 0. So these are actually different checks. EDC. So 1 is obtain Zelda's letter. So that's the flag we're looking for. So not this one. This is Pulled Master Sword, apparently. It probably affects text. I don't know. So it's one of these 2 functions is probably it, which isn't in the... Oh, they're like right next to each other. So that's one way. But before I delve in this way, I just want to quickly show you the other method I usually use. So let me tell you how to read the overlay files in general. So going back to here, we have this overlay file here. This is the range of files. So this is the range of data. The overlay header is going to be at the end of the file, not the start. Whatever. I don't know who decided that, but it's at the end of the file. So we actually want to look at the end file address, not the start. We could do the other way around, but so here's end of the file. It'll always kind of look something like this generally. There's going to be a number and then some 0 paddings usually, and then a bunch of these like patterns look kind of like this. But how it works is the last value tells you the size of the header. So it's 350 bytes. So we're gonna count starting from the end, 350 bytes. So this goes up 350. So this is the overlay of this file. So sometimes what I do here is I just open up Notepad and I start just copying things over. So this is the overlay below. There you go. So the first 4 bytes are the most relevant thing. These are the size of the sections. So the overlay file is split into like 4 sections. The first one is the code, which is generally going to be the most relevant thing and the biggest stuff. So that you can tell this, and this is the size of how big that section is. So the code section of this file is 2090 bytes. The second section is I remember these are two different kinds of just static variables. I'm trying to remember which one that is. I think the first one's like static data, and the second one is like it's like static read write data. One's read only, one's read write. I don't remember which one's which. And the last section, which I don't know if I've ever seen used or not, it's the zero section. Basically, when it loads the file, if there's any, it'll add on an extra number of bytes to the end of the file, just fill the zeros for additional scratch space the file can use. The first is data, the second is BSS. Yeah, I've never actually seen the zero data used in a file, but I'm sure it does come up. It's not super relevant, but anyways, that's the size. This last part here, all the rest of this is called the relocation data. This basically tells you where all the pointers. Remember talking when you load the file, it repoints all the pointers based on where it gets loaded in the RAM. This just defines where all those pointers are. But we don't have to really worry about too much unless you're like really feel like you need to do it. I guess I can say that for later if you are interested. But anyways, you go back to the beginning of the file here. So here's the beginning of the file. If you notice, right before the beginning of the file, there should be another header right from the previous file right above it. So you can see the same kind of pattern from the previous file because they're all back to back. But the first section is 2090 bytes, so it's pretty large. 2000. One more. There you go. So this is the code data, and we can go ahead and copy that in. And after that, we have 1C0, and all the overlay files, by the way, that I was looking at, like the one that this thing doesn't have, it only has the first section, which can be pretty annoying at times, and I'll get to that in a minute. It probably isn't relevant, but every once in a while this does come up. So the next section is 1C0. 1C0. These sections are usually fairly small. And the one after that is just D0. And then if you notice, we're right up to the overlay file again. So that's the entire file. The overlay section is kind of like the fifth section of the file, if you want to think of it that way. So we can go ahead and move it. Oh, hello? How did that even happen? So that's like the fifth section of the file, if you want to think of it that way. And there's just no zero section because this is empty. So this is the entire file. Usually the start of this section is you'll find that overlay, the actor header that I mentioned. The actors are kind of like specific to actors, not like a file system thing. But it's not. So it's probably this thing. Like I said, it's usually the very first thing. You usually see 4 pointers in a row. They're like 8-0 pointers. And that's like probably what this is. So we can actually check this if we. So like, for example, let's say we want to look at this address here. So the way I do it, I usually pull the calculator. Programmer mode is like amazing. So first we need to get this into ROM address because RAM address is basically useless and I don't care what MZX says. I like have never used it and it's really frustrating. Anyways, so we subtract it from the base RAM address, which is this. And then we add, and we look 290, that number should look familiar. We add this, so first of all, this is just 290. So there's 22090 from the start of the file. So we can either just count that many bytes from the start of the file. We can also just add the base ROM address and then jump to that location. And that also gets us there. Either way, this is the actor thing that we're looking at. But like I said, the only thing that really matters are these pointers here. And the first one is the most relevant. The first one, as I said, is the init pointer. That's the thing we usually care about. You might care about the main code. The main, generally in files, so the way actors are set up is that they have an init code that might call their functions, you don't know. Then there's a destructor, which usually does basically nothing. The destructors are usually uninteresting. The draw code is very complicated. I never understand it, but it's never relevant. But the main code is really short. Usually the main code, usually every actor has a pointer to some code to run. So it just keeps a pointer to the next instruction to run, next frame. And so the main code just calls that pointer. And then that code might change the pointer. So like the actors kind of have like a state-based system, like a state graph, where like they're in a state that's calling a particular function, and then that function might change to a different function to be called. And so it can be kind of hard to follow all the functions and what they do and the order they get called in and how the different functions call each other. But JLRA T9 is basically main. Yeah, exactly. So you'll see an instruction like JLR and then some variable. So we can go here, like, so the main is this variable here, right? And we can subtract the base, the RAM base, and then add this. And we can go to this address. So this is the main function. Usually it's a little hard to tell. I often just look for the telltale signs of the end of a function. No ops are pretty good. The other one is I think 03, because that's the J. That's a J. That's a JL or JR. Sorry. Yeah. So here's the 03, and here's a no op. And so I usually just open up so depending on what I'm disassembling, if it's really short like this, I just use Shellstorm because it works better. Hello? What are these extra checkboxes, and why did it disassemble nothing? Okay, well, the other site you can use is OOTA, which never works for me. This site goes down so frequently. Annoyingly, it assumes... So you can set the base address here if you wish. We'll just set 0 for now. And big endian. It always forgets big endian anytime you change anything. So anyways, here's the function. Oh, there's a little bit more. But you see as JLR19 or T9. So that's its call to the function. This main code is actually doing quite a bit. It has a bunch of JLs. So Mito, apparently, their main function is pretty hefty. Who knew? Not that it's super important yet. So this will keep going for some bit longer. It probably looks like it ends here because he has 0.3 here. And this 27 thing is in a add. So I think this is actually the end of the code here. But that's the idea. So the main code usually doesn't have anything interesting. You're just trying to follow this pointer is usually how it works. Mito's main is bigger. Mito's main is bigger than like any main I've seen before. Usually every main I've seen is like 8 op codes long. Anyway, so that's where they get this information from. So that's how they get the inits. Everything that's not one of the init destructors, main, or draw functions, they just label as some arbitrary number, just ascending by order that they are in the file, which is often not useful because it's not actually what you want. Also, this disassembly has a lot of other weirdnesses. Like, it doesn't do negative numbers really annoyingly. So like whenever there's stuff like up here, it's adding FFD8 to the stack pointer, which is dumb and annoying because it should just be negative 28. And the fact that I have to like do that is stupid. But that's the idea. Anyways, so that's the general. Once I have the actor file, sometimes I just disassemble the entire file in OOTA. One of the nice things about OOTA is that OOTA will this doesn't, because I guess it's too simple, but it'll draw like arrows showing you all the branches. And if you have all the data in here too, it'll like leave those pointers in. But one of the big things, like I said, is missing here is this section of memory, which isn't, and you notice here, it's just like a list of pointers. And it should be pretty obvious because a lot of times the way code works is that there's going to be something called a jump table. So the way it works is that the code will basically say like, hey, just jump to like the 8th like pointer in this table, right? And so like it's hard to know like where, and you notice there's a lot of duplicates in this list. But it's hard when you get those functions where it just reads a pointer from some address and then jumps to it. You're like, well, where even is that? So you have to look here to get those addresses, and that, like it's just missing from here. Anyways, so we have these two, or no, not those two. These two are the most likely culprits, right? They're checking for whether or not you've talked to well, whatever you have the letter or not, right? So this might affect like things like is she talking to you, like the dialogue you get and maybe where he spawns. One thing I could think of would be really easy for this is that since we don't really care about the dialogue being accurate or anything like that, if these just always returned false no matter what, then it wouldn't really be a problem. Like these Mito just will never be affected by that flag. So one option is just replace these and with zeros, these two spots, without even knowing what they do, and then whatever Mito's code is doing won't be checking for this flag anymore. That would be like one suggestion. Now, annoying, like I said, this code here doesn't really tell you that well, like where the stuff is. And usually you have to just disassemble to get the actual addresses because we need the actual ROM addresses to really work with this. In this file, does they give you the RAM addresses of the functions, which is nice, but it'd be kind of better. One thing I like about OOT is that it tells you the address of every instruction here. So you just want to replace a certain instruction, it tells you what that address is. You'll need to set the base address. So it starts at 0 because it's at 0. But if I said like set the base address to like say this thing here and then up, then they would all be starting at that address and just counting from there. For example, hey Amoeba. But that's the general gist of like how you read these files and how you like find what you want to find. Typically, I kind of disassemble the file, and if the init's really short, I might read through it, and then see if I can find the thing that I'm looking for. So let's like just try making this change here, I guess, and just zeroing out these two instructions without really looking at what they do because I'm pretty lazy. MZX is probably going to look at my code, a few days later and be like, this code's stupid. You're not zeroing out the right address. You're supposed to be zeroing out this other thing over here. It works better. And I'm like, whatever. And he can clean it up. But I don't really know how this file works. So it's like, I'm just going to just do the things that are obvious to me and just see if they work. And if it does, then I'm done. And if it doesn't, then we can like move from there. So this is the address we're looking at in RAM. So we're going to quickly try to get us into the ROM addresses. I mean, he gets mad every time you don't do everything in RAM addressing, which is like, how would you even do RAM addressing? Oh, whoops. No, please don't do that. So there's two function calls here, and I think it goes to about here. J? Oh, because it's in freaking Little Indian. Is this the right data? So one thing I hate about OOT is OOT puts everything in decimal for like all these ads, which is like, oh, why? So luckily here's the raw data. So like we're looking for like A5D0, like this right here. If you're not familiar with how opcodes are structured, that can help you read the byte data if like this is like weird. Particularly since a lot of times this A5D0 is going to be always split across two instructions. So here's the first half is A08012 and then A5D0 and when they split over these two instructions, instead of being 1-1, it's 1-2. And I can talk about why that is in a bit if you're interested. So a lot of times it's nice to read the byte data because when you're reading these instructions here, it doesn't help you. But here we have ED6, which wasn't what we were looking for. We're looking at EDC. Did I not? Oh no, ED6 right there. And then right below is EDC. So here's the EDC. And down here is another EDC. All right, so I think I grabbed a little too much code. Anyways, then we can set our base ROM address here. So we set our base address to this. Now all these instructions are in their actual ROM addresses here, which is nice. Yeah, I grabbed a little too much code. Here's the end of the function here. I grabbed like a third function right after that. Honestly, this is kind of a weird instruction, to be honest, but that's fine. So the two instructions you cared about is there's this and here, and there's this right after EDC, and then again here, there's an and here. So these are the two instructions we want. So here we open up, let's go open up our hacks. And we want to org to these two addresses. So I can't copy this, can I? Wow. Okay, well, we're just going to write it by hand. That's cool, I guess. .org ox. Oh gosh, these are in RAM addresses here. Oh, I have the other thing checked out. That's funny. It's like, why do I have like this craziness in my repo right now? Okay, thank you. Technically, it's supposed to be org A for RAM addressing and org for RAM addressing. But if you do RAM addressing, you have to define the mapping from RAM to ROM anyways. So I don't know. It's silly. Anyway, so we want E61B7C. Another one is this guy. OXE61BB4. And we're just going to write, the first one is this instruction here. So is this going to be and I T9, oh my God. Well, I could also just be load immediate T90, for example. If we wanted to. And this could be T3. Or if you want to maintain like the original kind of style, it would be and I. Oh my gosh. This is T3 with T2. And the other one was T9 with T8. And so now when we compile this, it should have actually like almost no change at all anymore. So it should be like a 1 byte change in those two places, which is kind of an advantage of keeping it similar. So if you look at our MIPS now, ROM patch.txt, yeah. So, oh, it writes out the whole word anyways. Okay, then it doesn't matter. I forgot we changed it to be whole words instead of bytes. Anyways, whatever. Do whatever you want. It's fine. And then we just rerun it and we see if there's any change. So that's like the general gist. So it's not too hard to find stuff that are like sometimes, like I said, in this case, there's an address that we're looking for and it was pretty easy to find it. And sometimes it's really hard to find the thing that we're looking for. And like I said, this is like a really easy tweak. We don't have to like, we're not adding any conditions. Removing conditions is a lot easier than adding conditions because you don't need to like add injections or anything or whatever. Output. I don't know if I have my controller. I do. Okay. Oh, I'm sorry, it's adult. That's interesting. Please don't do this to me. Okay. You think I set the base address wrong? That's possible. No, that's the right base address. This is the base address. It's the start of the file. I think. Oh no, it should be start of the section of code. You're right. So it should just be this address. 2948. Oh no, not endianness. Oh, it actually still fine. Amazingly. I wonder if they fixed that. Let me 2974. 2988. Good catch. Oh, I didn't do closed forest. Yeah, Mido's not going to be there. Testing is hard, man. It's hard to make sure your tests are accurate. I really should be starting as child. Okay, I am starting as child. All right, so ideally Mido should just be around in both spots. Yeah, I see his fairy or whatever. This is Mido, right? The real joke is when that's not Mido. Because it's not. That's the other kid. Yeah, it's Pokey. Well, that's fine. This is the guy we care about disappearing. Okay, so now what we want to do here is open the hex editor. For whatever reason, BizHawk's hex editor is like totally busted in 4-byte alignment. It just does not work at all. Do I add a new instruction with offs and adjust offsets in every instruction after that, or do you just replace no ops with new? So I don't like expanding files to like adjust things because it usually means that I have to include large amounts of vanilla code. Also, expanding files is really hard in OT because the files are usually back to back. So normally I try to just replace code. Typically, what we do though is in OT we just we expand the size of the ROM because we have the ROM can just be bigger, and then we have a section of code where we just created a new file, and we can just have as much space to write new functions as we want. And then if we want to inject code that involves adding more code that we can't do by replacing the original code or rewriting it in some way, then we add an injection where we're like it jumps to the new code, and then usually any code that we replace gets moved to our code, and then it calls back. So like a lot of examples are like usually a hacks is mostly just full of injections. And you look, most of these are just like jump to instructions, just various JLs. Occasionally, like here's like the original code, and then we replaced it with new code. But part of it includes the injection. Sometimes we just no op code just to remove instructions. And we usually try to document like what was there. But there are some places where we can just fit in the code in place. But typically we just have just a JL to the new code whenever we can. But like here, for example, we just replace the instruction. This just changes the size requirements that the guide checks. And so we just change those numbers. And so like, if you look at some of these instructions here, so like say fishing, you would call something called initial fishing. This isn't a good example. There's usually something called here. So they're obviously called displaced code. So this is the instruction that got removed to add the jump to this code. And so in this function call, we put in the code that we deleted, making sure to maintain whatever registers are supposed to be maintained. But that's like generally the structure of how we do injections for OT. All right, so we're looking for 11A5D0, which is save context plus EDC, I think was what it was. So we go to this address. This is the byte. So right now it's not set. So we set this to 89. So now the flag's set. You still complaining about sword and shield? And I guess we'll probably have to reload the room. I wish my emulator was faster. I still see him over there, so something worked. So that seems to have worked. And then just to verify if we remove these instructions and just test it again just to make sure that this actually worked correctly. We have a disassembly of the game. Yes and no. There are disassemblies of the game, but they aren't very good. They're sometimes good and sometimes not. I typically have to disassemble stuff myself though. All right, so this he should still be complaining about the sword and shield. And now if I set this to 89, hopefully he'll despawn. Assuming that this was done correctly. Hopefully this is even the right address. I don't even know. I don't even know if it's the right address. Still see him. Oh, well, there's a flag where when I've talked to him. Okay, well, that's the wrong address. What is it supposed to be? EDC. Oh, it's probably EDD. It's probably loading 2 bytes, isn't it? Yeah, half. Oops. So this should be 21. Sorry. For some reason, I just assumed it's loading byte. It's really, I was not really just paying attention, honestly. I'm just kind of just, like, since this is, like, generally a fairly minor fix or whatever, it doesn't take me, like, I kind of usually rush through it and then make mistakes. All right, he's clearly gone, right? He's gone. So let's go ahead and test again. Oh, we already have a test. Here you go. I still go to Link's house to reload. Look, man. Oh no, it's gone. Okay, he's still here. Got it. And just to make sure, we're going to give myself all the items and see if having the item in your inventory causes him to despawn as well. Okay, he's still there. The other flag was Pool the Master Sword, which he seemed to check for, which was at 2-0. Oh, that's already set. Okay, yeah, then he doesn't care about that. Because that's set so that it skips the cutscene. Does Hylian Shield work? No, it doesn't. That's pretty funny, actually. I wonder if that's in logic. All right, so that works. So here you go. I can give you the code. Just dump this into the... There you go. You can also make it a load immediate 0 if you wish. It doesn't have to be this and or whatever. Hey, you know something about MIPS, you can use that knowledge. Must use that power only to destroy. Okay, so kind of like, I guess, continuing on the train of modifying actor files and MIPS in general. So something you need to be careful about is if your cycle doesn't load immediate. No, it's the same. So MIPS, the pipeline likes to do instructions simultaneously. So typically, because of pipelining, so typically every instruction is actually the same time. So every instruction takes, in general, the same amount of time to complete. There are exceptions though. Multiply is slower, and divide is very slow, and floating point, blah blah. And some instructions can do it, but the way that the CPU works is that instructions will end up halting. The other main thing is something called data dependency. So because it likes to do the instructions at the same time, if you're running instruction and the next instruction depends on the previous instruction, then the CPU will actually wait until the previous instruction is ready before continuing to the next one. So, for example, here, so when we're loading this address, because MIPS is all instructions, you only have like 2 bytes for the immediate. So this is a 4 bytes, so it needs to be done 2 instructions. So first we load the 8012, and then we load the bottom half in 2 instructions. But you notice that there's an instruction in between these 2 instructions. In this case, it's a branch. But the idea is that now, by the time it gets to this 3rd instruction, this instruction is fully completed, and it can do this instruction without waiting. So whenever you do, and the reason is, so whenever you are using a variable that's being written to, to save time, you would like to put instructions in between. So a compiler usually rearranges your code a little bit to automatically like reduce the amount of data dependencies. In general though, like I said, we're talking about like a single pipeline cycle that's being saved here. So it's really minor, and in general, let's talk like optimizing code here at a pretty low level. But it is a thing to keep in mind. Similarly, putting things in the branch delay slots, it's like instead of putting a no op, you could do an instruction here. So it like loads the save pointer here, and then by the time this branch is taken, whether it's taken or not, it'll be fully like loaded at that point. So there's like stuff like that that are pretty minor. I usually don't worry about that stuff when writing ASM because personally I find it makes code harder to read. And I care way more about making your code readable than making it fast, especially since these kind of optimizations are so minor that they really don't make a big difference. Like this really only kind of saves time when you're just doing this everywhere. You have like a large project and you're like having these tiny time saves just throughout your entire project. But when you're just writing a piece of code, it doesn't matter. It really doesn't. It's like, so I wouldn't really bother. Unless it's like really heavy code and you're like really trying to optimize the shit out of it. But there's so much buffer in like CPU time that it like never, those kind of things never really cause lag. I mean, cause like with most games, like you have the amount of time to fill the whole frame of processing time. So like if you end up adding processing time to the frame, as long as you don't like go over the length of a frame or the V blank really, then you won't actually lose any time because your CPU is usually idling for some portion of the frame anyways. So I usually don't really worry about it too much. So that's like one thing to keep in mind. But the other thing I was going to talk about here is the relocation. So I mentioned in the beginning that there's this relocation table. So here I went ahead and grabbed all the data for this file by the sections. And this last section here for this header, technically the way this works is this says there's CC entries. So technically this and here's the table, and this is probably some padding going on here. And so this is each one of these entries is there should be CC of these relocation entries. Now they're kind of annoying because the way they're structured is you can look it up, but I think the first nibble is like the section that it's in, or like the top 2 bits, or like the section that's in. And there's like the other one after that is like the type of relocation it is. So there's actually, if you really care, it's actually documented here, but you can also look, it's just a general MIPS thing. It's not like an OoT thing. So you can find it elsewhere. Yeah, so here's the 5 sections of the file that I mentioned. BSS. This is like the 0 data. And like I said, I've never really seen it used really. Anyways, so these are so the beginning will have, yeah, so here the first 2 bits are the section it's in. So one of these 4 sections it refers to. And then there's okay, well the whole rest of that byte is used up for the type. Even though there's only 4 yeah, there's only like 4 types. Anyway, so it's gonna be one of these values. There are other values that relocations can be, but they are never used by OT. So these are the only ones you actually care about. And then the rest of it is the actual offset. So the way it works is like the way you'd read it, for example, like let's say this first one here. So the top 2 bits of 4, 5 is going to be 0, 0. So if you don't know how to read binary, you just type in 4, 5. So there's 1 bit set. So now this is going to be in section 1. I think it's indexed 1 for whatever reason. Yeah, index 1 is section 1. Don't know why. I don't know what section 0 is, but whatever. Section 1. So this is for section 1. Then we have 5. So it's going to be a MIPS high 16, which I'll get to these types in a second. And then the rest is 3C. So if we go to, so section 1's this. We go down to 3C. Well, actually, the easiest way to do this would be the actual ROM. I lost it. ENMD. How much did I say it was? 3C. It's always going to be a multiple 4, by the way, because instructions are always 4 byte lines. So right here, it's this instruction here. And we look at it. I don't know why Shellstorm's not working. Yeah, maybe it's because I have this on. Oh, MIP 64. I don't get it. I don't know, whatever. So if you look at the instruction here, it's a load immediate 8080. So this is actually the first half of a pointer instruction. It's usually pretty obvious because it starts with an 8. So generally RAM addresses will always start with an 8. But we actually look for there should be one following this afterwards at 40. So that's actually the next instruction. So we can grab that too. Big. Give me, thank you. So here's the full, is loading both the halves into A1. And if you look at this address here, it's 808E4958. Now, one thing that you should be careful about this. So usually when you're loading an instruction loading an address over to instruction, it always does load upper immediate. So it loads the upper half, and then it adds the bottom half. So I don't know who designed MIPS and why it's designed this way, but add is really stupid because you're adding a number. So now there's overflow. So if this number is greater than 8,000, it means it's negative, which means that if you add these two numbers together, it'll subtract 1 from the upper half because of math. So because this number is less than 8,000, it's 495E, it doesn't subtract. So this address is 80AE and 4958. So this is the address that's being loaded in A1. If this bottom half was greater than 8,000, then we would have to subtract 1 from this. If they did OR, this wouldn't have been a problem, but because it did AND, it has this issue. And I don't know who designed MIPS, but it's it's MIPS itself. It's like the whole architecture is dumb. I don't fucking know. Anyway, so this is address. And if you notice that anything's an address, if the address is in this file, then it's going to be relocated because these are all pointers to these addresses. And we actually notice this RAM address. If we look at the RAM ranges, this value AE495E is between these two values. So this is addressed into this file. So that is another clue that this is what it is. Anyways, what ends up happening is here is, so this is basic. I'm just showing you how this is a reference to all the pointers. And the pointers there might be in two types. So in here, they could be in like these two halves where they load into the two half instructions. But there's also a jump instruction, and there can also just be a full 32 byte word. Oh, I'm just using this add-on called Dark Reader. It works okay on some sites and terribly on others. So I've had to disable on half the sites I've been to. But yeah, dark themes are cool. Anyway, so that's the general idea. But the point is that when it loads this file, it goes to all these pointers and modifies the data that's there based on where it gets loaded in the RAM. So if you want to modify any instruction that's at any of these pointers, at any of these addresses, then you have to remove it from the relocation table. And that's actually kind of difficult to do because you basically have to rebuild the whole relocation table. So instead, what I do is just avoid those instructions. I think you use a number of cases, like I think in Malin, I didn't write this code, but this code was pretty heavily commented. It's also got a lot of comments in it. Yeah, so for example, these instructions here, for whatever reason, were deemed unsafe. And so these were the original instructions and weren't changed. Something like that. And so they try to like work around the code that exists without modifying any of these relocated file instructions. The older version messed with relocation ops. Yeah, I don't know. But that's the idea. They're usually pretty easy to identify. If there's any pointers in your code, they're almost always going to be relocated as long as those pointers are within the file that you're working with. So they're pointing somewhere in the file. What basically means is if they're like a really low address, they usually aren't in the file. So if you look at the file list, typically pointers will always be pointing within the function that you're in. So they're going to be like whatever the range is. If it's anything in this higher area, especially code, this range is really common. It's pointing to that area, then those are not being relocated because it's not in the same file. It's only pointers that go to the same file that are relocated. Similarly, if you want to add an instruction that points to something in the file, it needs to have a relocation added to it. And again, adding and removing relocations is pretty hard. So I would say that generally avoid doing that kind of stuff because it's a huge pain in the butt. I actually wrote this crazy code in Python of all languages in mq.py. So in here, there's kind of a file descriptor in here. And one thing that's in here is something that can read all the relocations. And so you can tell it to read a file and you can say like, hey, add some relocation entries to the table or like insert space. Yeah, it would be easier if we use a disassembly, but I wanted to avoid including the original code of the actor. This was like to reduce the amount of code that we had to pack with the randomizer as much as possible. That was like vanilla, which is why it ended up being like kind of absurdly complicated for what it was. But yeah, that's the general gist and things to look out for. The relocations are like the big gotchas because a lot of times what I found was that I was testing on like emulator and like I was like when I first started, I was writing over relocations lines, and when I loaded in the emulator, it worked fine. I don't know why. However, the emulator handles relocations tends to seem to ignore them in some fashion. So like when I was testing on emulator, even though I was deleting all these, like overwriting all these unsafe instructions that the game modifies after the fact, it still worked fine. But if you test it on like Virtual Console or on the N64, it crashed. And so that was like a common problem because I only have a way to test on emulators. So like I would like write code that seemed to work fine, and then I would push it, and then it crashes for other people who are playing on other systems. So it was pretty problematic. Anyways, that's all I have time for. I will head out now. I hope this was informative and all that and whatever. But good luck on your MIPS stuff. I have meetings to go to. I'll probably be back later tonight. I'll probably be working on Metroid stuff though. I might try to get some of these short PRs in, but most likely I'll just want to work on more of the Metroid editor stuff. Yeah, sorry, MZX. I know you just got here. There was also a short stream. It was like only like an hour. But yeah, I'll see y'all around, and thanks for stopping in.